Yeah, I decided to split out under signal transduction stage 2 the second messengers because there's just a lot there and it's kind of complicated. So you dealt with the phosphorylation cascade and the two-component regulatory system, both very important, very common. But let's take a look at what happens when we really want to amplify the signal. And we're going to make use of something called a second messenger. So a second messenger is, for example, cyclic AMP, is a molecule that is either produced in rapid high quantities once the receptor is activated, the original receptor is activated, or in some cases, like with a ligand-gated ion channel, it's simply the flood of ions rushing in. So where there was a small number of hormone molecules that initially opened the ligand-gated ion channel, there's bazillions of ions rushing in, and those ions are then going to interact with various response proteins and cause a very rapid response. So let's take a look at how cyclic AMP works. Cyclic AMP is a really important second messenger. It's going to be produced through a G protein coupled receptor system. So our receptor is a GPCR. Some kind of a molecule, a signal, is going to bind the GPCR, which will then bind to the G protein. The G protein then we know separates out into its alpha subunit carrying GTP and its beta gamma subunit as well. One or the other or both could potentially theoretically act as the next step in the signaling process. The activated G protein, in this case it's going to be the alpha subunit, is going to interact with another peripheral protein called adenylyl cyclase. And adenylyl cyclase takes ATP and turns it into cyclic AMP. I'll show you what that molecule looks like in just a minute. Cyclic AMP, and because adenylyl cyclase is an enzyme, it can make gobs and gobs of cyclic AMP, right? So only a couple molecules of the signal may have reached the GPCR, but now we're going to make thousands upon thousands of cyclic AMP molecules to amplify that signal very, very rapidly. The cyclic AMP then interacts with a soluble protein kinase we'll simply call PKA, protein kinase A, which can then phosphorylate and thereby activate the various cell response proteins that we haven't talked about yet, but they're in the next video, things like enzymes, transcription factors, or structural proteins. The beauty of this system is that as quickly and as explosively as it can be activated, it can very quickly be drawn back in. It can be reversed. So cyclic AMP itself is always being degraded by an enzyme called phosphodiesterase. And so even though adenylyl cyclase is trying to make all of this, if adenylyl cyclase stops making cyclic AMP, within a couple of minutes there's none left because the phosphodiesterases are very quickly degrading it. And at the same time, the phosphorylated proteins like PKA and the various phosphorylated response proteins are being dephosphorylated by enzymes called phosphatases. So you've got kinases like PKA on one hand, you've got phosphatases on the other. Kinases are phosphorylating and activating some kind of response protein, and phosphatases are dephosphorylating them. So that if the signal that triggered this whole process is degraded or decreased dramatically, the GPCR will go back to its normal conformation, G protein will go back to its normal conformation, adenylyl cyclase will stop making cyclic AMP. What cyclic AMP was there will very quickly be degraded by phosphodiesterases, and any of the phosphorylated intermediates like PKA and the cell response proteins that have been activated with phosphates will be inactivated by the phosphatases. And in a matter of seconds to minutes, this whole massive response can be drawn right back in again and things can go back to normal. It's a really amazing system. This molecule here is cyclic AMP. I just want you to have a visual. So hopefully by now you guys recognize you got a nitrogenous base out here. That's the adenine nitrogenous base. Here we've got a ribose sugar, not deoxyribose because there's the hydroxyl right there, but a ribose sugar. And normally coming off this carbon here, you've got your phosphate group. Here's your phosphate, but then that phosphate has been cycled, if you will, where this was an OH and now it's bonded to this CH here. And so we've got a little bit of a cyclic action going on over here, and this is what's called cyclic AMP. This is one of the most important second messengers you'll see. So let's take a look at an example. Or I guess it's more of a model, and then we'll look at an example. So here's our G protein coupled receptor. It binds the signaling molecule, gets activated, causes the G protein beta gamma dimer to separate from the alpha subunit. The alpha subunit, which now ditched its GDP for a GTP, that's where it gets its G protein name from, now has a GTP. It physically interacts with this adenylyl cyclase and activates it. Adenylyl cyclase just starts churning through ATP, creating gobs of cyclic AMP, which can all then activate protein kinase A. Protein kinase A then, now that it's activated, can phosphorylate its targets. And its targets are the various things we'll talk about in the last video that ultimately lead to the final cell response. So what's the benefit of a second messenger? And how can it be reversed? Make sure you recognize this. Okay, let me give you a real-life example of a benefit. So you're out in Yellowstone, and you come across Yellowstone Falls, and you're taking a picture when all of a sudden this guy photobombs you. Ah! Right? Great big grizzly bear. What's your response? You should have this massive fight-or-flight response, and it needs to be pretty much instantaneous, right? We don't want it to be this slow, gradual response. We want this to be within one heartbeat. You go from 30 beats per minute. That would be bad. You go from 60 beats per minute to 120 beats per minute, right? And you go into this total fight or flight so that you can survive. And then as soon as the bear turns around and walks away, you don't want to stay in that intense fight or flight for the next hour, 5 hours, 24 hours, the week, right? You need to calm back down again. That's the beauty of using these second messengers. So your signal receptor complex, just a single signal with a single receptor, leads to lots and lots of cyclic AMP. We call that amplification. And then all that cyclic AMP activates lots and lots of protein kinase A. And each of those enzymes can activate lots and lots of whatever the target proteins are by phosphorylating them. So very rapidly, a single signal molecule can induce a massive response within the cell. Let's look at one example of what adrenaline does in a muscle cell. It does other things as well, but here's the GPCR, that is the epinephrine or adrenaline receptor. It gets activated, interacts with the G protein that was alpha, beta, and gamma. The beta gamma separated from the alpha kicked out GDP, replaced it with GTP, slid over and interacted with an adenylyl cyclase that starts churning out cyclic AMP, starts activating massive numbers of copies of protein kinase A, which then starts activating massive numbers of copies of response proteins that can carry out and begin to carry out the response. In this case, they're showing how it starts breaking down glycogen into glucose and making sure that the enzymes that take glucose and make glycogen are paused, so that lots of free glucose is available for the high energy needs that you're going to have as you try to run away from that giant grizzly bear. Okay, second messengers. Really important when what we need is a gigantic response and we need it really rapidly, and we need to be able to pull it back in again just as rapidly. So I hope that was helpful. The very last video, guys, is going to be all about those cell response proteins. I'll see you in a minute.